Download this code from codegive.com, link in the description below. OK, let's dive into boundary value problems, BVPs, with a detailed explanation and code examples, primarily focusing on Python. What are boundary value problems, BVPs? In the realm of differential equations, we encounter two primary types of problems. One, initial value problems, ivps. These problems specify the state of the system at a single point in time, usually the initial time, t equals 0, and seek to determine the system's behavior forward in time. Think of launching a projectile. You know its initial position and velocity, and you want to predict its trajectory. Two, boundary value problems, BVPs. These problems specify conditions at two or more different points. In the case of differential equations, the values or derivatives of the unknown function are given at the boundaries of the domain. Think of a hanging cable. You know the positions of the two fixed endpoints, and you want to determine the shape of the cable in between. Key differences summarized. Feature initial value problems, IVPs, boundary value problems, BVPs. Conditions at a single point, conditions at multiple points. Time/domain evolution forward in time defined over a domain/interval. Solution unique, usually, may be unique, multiple, or none. Stability generally more stable, can be more sensitive. Examples: projectile motion, radioactive decay, hanging cable, heat distribution in a rod. Why are BVPs important? BVPs arise frequently in engineering, physics, and other fields when dealing with systems that have constraints or are fixed at specific locations. Here are some examples. Heat transfer, determining the temperature distribution in a solid rod with fixed temperatures at both ends. Structural mechanics, calculating the deflection of a beam supported at both ends under a load. Fluid dynamics, modeling the velocity profile of a fluid flowing through a channel with fixed boundaries. Quantum mechanics, solving the Schrödinger equation with boundary conditions to find the energy levels of a particle in a potential well. The anatomy of a BVP. A BVP typically consists of the following components. 1. Differential equation, an equation relating the unknown function and its derivatives. This describes the relationship governing the system. It could be an ordinary differential equation, ODE, or a partial differential equation, PDE, but we'll focus on ODEs for now. 2. Boundary conditions, conditions imposed on the unknown function or its derivatives at the boundaries of the domain. These conditions specify the values or behaviors at the beginning and end of the interval. There are different types of boundary conditions. Dirichlet conditions, the value of the function is specified at the boundary. Example, y, a, equals a and y, b, equals b, where a and b are the boundaries, and a and b are given constants. Newman conditions, the value of the derivative of the function is specified at the boundary. Example, y, a, equals c and y, b, equals d, where c and d are given constants. Robin conditions, mixed conditions, a linear combination of the function and its derivative is specified at the boundary. Example, alpha y, a, plus beta y, a, equals e and gamma y, b, plus delta y, b, equals f, where alpha, beta, gamma, delta, e, and f are constants. Methods for solving BVPs. Unlike IVPs, which can often be solved using explicit forward-stepping methods, like Euler's method or Runge-Kutta methods, BVPs are more challenging. They typically require iterative or global methods. Here are some common approaches. 1. Shooting method. Asterisk treat the BVP as an IVP. Asterisk guess initial conditions at one boundary that are not specified. Asterisk integrate the ODE forward using an IVP solver. Asterisk compare the solution at the other boundary with the specified boundary condition. Asterisk adjust the initial guesses iteratively until the boundary condition at the other end is satisfied to a desired tolerance. Asterisk the core idea is to shoot trajectories from one boundary and adjust the aim until the trajectory hits the target at the other boundary. 2. Finite difference method asterisk. Asterisk discretize the domain into a grid of points. Asterisk approximate the derivatives in the differential equation using finite difference approximations, example forward, backward, or central differences. Asterisk convert the differential equation into a system of algebraic equations. Asterisk solve the system of algebraic equations to obtain an approximate solution at the grid points. Asterisk this method turns the differential equation into a set of discrete equations that can be solved numerically. 3. Finite element method, FEM. Asterisk divide the domain into smaller elements. Asterisk approximate the solution within each element using basis functions, example polynomials. Asterisk formulate a weak form of the differential equation. Asterisk assemble the element equations into a global system of equations. Asterisk solve the global system of equations to obtain an approximate solution. Asterisk FEM is more versatile than the finite difference method, especially for complex geometries. 4. Collocation method asterisk. Asterisk choose a set of basis functions to approximate the solution. Asterisk determine the coefficients of the basis functions by enforcing the differential equation at a set of collocation points within the domain. Asterisk satisfy the boundary conditions. 5. Spectral methods asterisk. Asterisk similar to collocation methods, but use global basis functions, example Fourier series, Chebyshev polynomials, that are defined over the entire domain. Asterisk often provide very high accuracy for smooth solutions. Python code examples. Let's illustrate the shooting method and finite difference method with Python code using SciPy and NumPy. Example 1, the shooting method. Let's consider the following BVP. The analytical solution is y, x, equals sin, x. We'll use the shooting method to approximate this. Key improvements in this version. Asterisk clearer ODE system definition asterisk the ODE_system function now clearly defines the system of first-order ODEs equivalent to the second-order ODE. It takes the current values of y and returns their derivatives. Asterisk function for solving IVP asterisk the code now encapsulates the IVP solving into the solve_IVP_for_guess function. This makes the code more modular and easier to read. It takes the initial derivative as input, solves the IVP using solve_IVP, and returns the value of y, pi/2, which we want to be equal to 1, our boundary condition. Asterisk root finding asterisk the solve function from scipy.optimize is used to find the initial derivative that satisfies the boundary condition at x equals pi/2. The lambda function creates an anonymous function that takes the initial derivative as input, solves the IVP, and returns the difference between the solution at x equals pi/2 and the desired boundary condition, 1. The root, where the difference is 0, is the correct initial derivative. Asterisk solving with correct initial condition asterisk after finding the correct initial derivative, the code solves the IVP one last time using that derivative to obtain the final solution. Asterisk accurate plotting asterisk includes a more refined set of x values for plotting, to ensure a smooth and accurate representation of the solution. Uses solution.sol to get the y values directly from the solution object returned by solve_IVP, ensuring greater accuracy. Asterisk analytical solution comparison asterisk the analytical solution y, x, equals sin, x, is plotted alongside the numerical solution for comparison. Asterisk clear labels and title asterisk the plot now includes labels for the x and y axes, a title, and a legend. Asterisk output asterisk prints the found value of the initial derivative to the console. Explanation asterisk 1. Conversion to a system of first-order odes asterisk a second-order ode needs to be converted into a system of two first-order odes for use with solve_ivp. We let y1 equals y and y2 equals y. Then, y1 equals y and y2 equals y. Since y equals y, we have the system. Asterisk y1 equals y2. Asterisk y2 equals y1. To solve_ivp asterisk this function is a powerful IVP solver in SciPy. It requires the following arguments. Asterisk ode_system, the function that defines the system of odes. Asterisk 0, np.py/2, the interval over which to solve the IVP. Asterisk initial_conditions, the initial conditions y, 0, y, 0. We know y, 0, equals 0, but we guess y, 0. Asterisk args equals initial_derivative, this passes the initial derivative to the ode_system function. 3. Shooting iteration asterisk the core idea is to adjust our guess for y, 0, until y, pi/2, is equal to 1. Solve does this automatically. Example 2. Finite difference method. Let's consider the same BVP. We'll discretize the interval 0, pi/2 into n equally spaced points and approximate the derivatives using central differences. Key improvements and explanations. Asterisk clear structure asterisk the code is well structured with a function finite_difference_ method that encapsulates the entire solution process. Asterisk boundary condition incorporation asterisk the boundary conditions y, 0, equals 0 and y, pi/2, equals 1 are now correctly incorporated into the system of equations. Since y, 0, equals 0, we don't need to explicitly include it in the matrix equation. However, y, pi/2, equals 1 affects the right-hand side of the equation. Asterisk internal points asterisk the code focuses on solving for the values at the internal grid points, excluding the boundaries, which simplifies the matrix setup. Asterisk matrix construction asterisk the A matrix is constructed using a loop, correctly implementing the central difference approximation of the second derivative. The structure now accurately accounts for the tridiagonal nature of the matrix. Asterisk solve function asterisk the solve function from scipy.linalg is used to efficiently solve the linear system of equations ax equals b. Asterisk step size calculation asterisk the step size, h, is calculated based on the number of internal points, n, ensuring that the boundary conditions are placed at the appropriate locations. Asterisk analytical solution asterisk the analytical solution y, x, equals sin, x, is plotted alongside the numerical solution for comparison. Asterisk plotting asterisk the numerical solution is plotted with markers at each grid point to visualize the discretization. The x-axis is correctly scaled. Asterisk comments asterisk the code is thoroughly commented to explain each step. Explanation asterisk 1. Discretization asterisk we divide the interval 0, pi/2 into n plus 1 subintervals, creating n internal grid points where we need to solve for the approximate solution. 2. Finite difference approximation asterisk we approximate the second derivative using a central difference. Y, x_i, y_i1, 2y_i plus y_i plus 1, /h_2. Where y_i is the approximation of y, x underscore I. Asterisk h is the step size. 3. System of equations asterisk substituting the finite difference approximation into the differential equation y, x, plus y, x, equals 0 at each internal grid point, we get a system of n algebraic equations. Y underscore I1, 2 y underscore I plus y underscore I plus 1, slash h caret 2 plus y underscore I equals 0. This can be rewritten as y underscore I1 plus, minus 2 plus h caret 2, y underscore I plus y underscore I plus 1 equals 0. For matrix representation asterisk we can represent the system of equations in matrix form as I equals b, where asterisk A is an nxn matrix with diagonal elements equal to, minus 2 plus h caret 2, off diagonal elements equal to 1, and all other elements equal to 0. This is a tridiagonal matrix. Asterisk y is a vector of length n containing the unknown values y underscore 1, y underscore 2, y underscore n at the internal grid points. Asterisk b is a vector of length n that incorporates the boundary conditions. In our case, b is mostly 0, except for the last element, which is equal to y, pi slash 2, equals dash 1 to account for the boundary condition at the right end. 5. Solving the linear system asterisk we use scipy.linalg.solve to solve the linear system I equals b for the unknown vector y. 6. Incorporating boundary conditions asterisk after solving for the values at the internal grid points, we add the boundary conditions y, 0, equals 0 and y, pi slash 2, equals 1 to complete the solution. Choosing a method. Asterisk shooting method asterisk suitable for lower order odes with simple boundary conditions. Can be sensitive to initial guesses. Asterisk finite difference method asterisk more robust than the shooting method. Works well for linear BVPs. Can be less accurate for problems with rapidly changing solutions. Asterisk finite element method asterisk ideal for complex geometries and problems with varying material properties. Asterisk collocation and spectral methods asterisk can achieve high accuracy for smooth solutions. Important considerations. Asterisk existence and uniqueness asterisk BVPs don't always have solutions, and if they do, the solution might not be unique. The existence and uniqueness of solutions depend on the specific differential equation and the boundary conditions. Asterisk stability asterisk numerical solutions to BVPs can be sensitive to errors, especially when using the shooting method. Asterisk convergence asterisk the finite difference and finite element methods converge to the exact solution as the mesh size, step size, decreases. Further exploration. Asterisk nonlinear BVPs asterisk these require iterative methods, such as Newton's method, to solve the resulting nonlinear system of equations. Asterisk higher order BVPs asterisk these can be handled by converting them into systems of first order equations. Asterisk partial differential equations, PDEs BVPs also arise in the context of PDEs. Example solving Laplace's equation with Dirichlet or Newman boundary conditions. The finite difference and finite element methods are commonly used to solve PDE BVPs. Asterisk libraries asterisk explore libraries like FENICS and PyFR for more advanced finite element analysis of PDEs. This tutorial should provide a solid foundation for understanding and solving boundary value problems. Remember to experiment with the code examples and explore different methods to gain a deeper understanding of this topic.